So let's talk about how ice sheets and glaciers form in mountainous regions and in the cold regions of the planet. So let's start with glaciers. And glaciers normally form in mountainous regions made up of both ice and firn and snow, which is covering it at the top, as well as recrystallized water from rainwater, or water from the snow, which is melted maybe in the warm days or in the summers and then refrozen. And glaciers form in the upper regions of mountainous regions in these bowl-shaped depressions, which we call cirques. These cirques are actually formed by the erosion of the rock by the ice, this mechanical plucking or ice plucking, where when you have water or ice which melts and fills up cracks in the rock and then freezes again at night or in the winter, it actually breaks up the rock and we get these bowl-shaped depressions which are filled up with ice and snow. On the left we can see one which is now empty of the snow. On the right you can see some of these which are filled with ice and snow. And this is what starts the glaciers, because eventually this mass of ice will be driven down to the lower areas by gravity, pulling this ice to the lower areas of the mountains. When we have all these valley glaciers merge to the lower areas moving towards the sea level, they'll all merge into a large cake-like mass which we call ice sheets, where the sheet can cover very large areas, horizontal areas. Maybe we'll only see the peaks of the mountains which will stick out from the ice sheets, and they will flow by gravity to the lowest point, which is normally sea level. Today, as I mentioned before, we only have two large ice sheets on Earth. One is the Antarctic ice sheet, which covers about 12.5 million square kilometers, and the Greenland ice sheet, which is about 10 times smaller, about 1.7 million square kilometers. And we also have what we call ice caps, which are kind of small ice sheets. They're disappearing fairly quickly. We used to have an ice cap on top of Mount Kilimanjaro, even in Africa. But with climate change, these are disappearing very quickly. So if we look at these ice sheets, which are basically in Greenland and Antarctica, there are these huge masses of ice which have collected from the mountainous regions, the glaciers. They flow towards the ocean, and when they get to the ocean, they actually flow over the ocean water, and then we call them an ice shelf. So the ice shelf is actually part of the ice sheet, but underneath the ice shelf, we actually have the ocean. So the ice shelf is floating now on the water, and the biggest ice shelf today is the Ross Ice Shelf in Antarctica, about 500,000 square kilometers. It's about 700 meters thick on the land side of the ice shelf and about 250 meters on the ocean side, on the ice front. And normally the ice shelves, they also connected to the continental regions around the ice shelf. So we normally have a bay which is connecting and supporting the ice shelf on three sides. But the demise of the ice shelf, the breaking up of this ice shelf, is normally through mechanical motions of waves of the ocean, the buoyancy of the water pushing up the ice shelf, and we get this mechanical breaking up we call calving of the icebergs, where we actually produce icebergs, which will then move away, float with the ocean currents, normally to warmer waters and eventually to melt. So the disintegration of ice shelves can be also natural by this physical, mechanical breaking up of the icebergs and the ice shelf. And as the water can warm as well underneath the ice shelf, we're now seeing that global warming and the warming of the oceans can also have a large impact on the disintegration of ice shelves, and we'll talk about that a little bit more today. So here's an image of the Ross Ice Shelf. You can see on the map the location, the little red X, and you can see this image showing part of the Ross Ice Shelf, which is again floating on the ocean. You can see the mountains in the background, where the ice shelf is connected to the continent. But as it moves into the ocean, the ice sheet, we produce this ice shelf, which has a lot of the ice below the water, and we can see these tens or 100 meters of ice even above the sea level. Now, when we talk about ice sheets and even glaciers, there's a certain dynamics which has occurred. Things are happening all the time. Things are moving all the time. And we can divide up the ice sheets and glaciers into what we call the accumulation zone, where we're accumulating mass, and the ablation zone, where we're losing mass. And we can see in this image here that obviously at the top of the glacier and the ice sheet, where we have lots of snowfall and it's way below 0 degrees, we're adding mass by snowfall, and this is the accumulation zone. And when we go to lower levels where it's getting warmer and we're also having this calving effect in the oceans, we're losing mass and we're actually decreasing the amount of ice which we have in the glaciers or the ice sheets. And if we have a balance between these two, so we're adding the same amount of mass that we're losing, then the glacier or the ice sheet will be stationary. It's not going to move. But if we're putting in more mass than we're losing, it's going to keep on moving into the ocean, and we're going to see it get extending in the length of the glacier, moving down to lower elevations. On the other hand, if we're losing more than we're putting in at the top, then we're going to have a receding of the glaciers and the ice sheets, and we're going to be losing mass overall. And this is what we're seeing around the globe. If we look at this table here, the numbers here represent the mass balance on a yearly basis. What is the mass? How much mass are we gaining or we losing overall every year, per year? And if the numbers are negative, it means we're losing. It means that we're losing more mass than we're putting in. If they were equal, if we're getting the same input as output, the numbers would be 0. But if we have negative numbers, it means we have a negative mass balance. And we're seeing this in basically all the glaciers around the globe, or 99% of the glaciers, which are receding. They're getting smaller. We have a negative mass balance because we're losing more mass than we're putting in because the climate is getting warmer, especially the summer temperatures. Glaciers and ice sheets in the winter are much below 0, so there's no problem with the winter temperatures. But as the summer temperatures are getting warmer in the Arctic, in Greenland, and in Antarctica, we're seeing more melting in the summer months and less additional snow coming to balance this in the winter. I should point out that you can even see on this plot that there's one place where we do have a positive number, and there are a few places in the world where we do have positive numbers, but that's because even though the temperature may be warming, we're having more snowfall there, and the warming from minus 30 degrees to minus 20 doesn't result in the melting of the ice sheet. If we look here at this global changes in glaciers around the globe, the mass balance, this represents how things are decreasing in the thickness of the ice on the glaciers on an annual basis. From 1970s, we can see that all the glaciers are getting thinner and thinner because they're melting away, and it appears also to be accelerating with time. That it's not a linear change, that things are increasing with time, and on average we can see about 25 meters decrease in the thickness of glaciers on a global scale. If you go visit Greenland in the summer, this is what you'll see. You can see from horizon to horizon we have the ice sheet, which again is a few kilometers thick, but then you see these moulins, these meltwaters, melt ponds, which are because of the warm temperatures, and the water can actually drill a hole through the ice sheet, and you have these waterfalls which will go for maybe 2-3 kilometers through the ice until it hits the bedrock and then flows to the ocean and will get into the ocean and has obviously then a direct impact on sea level rise. We'll talk about that a little bit later, but basically the ice which is sitting on the land areas, as soon as this melts and we have a negative mass balance, this water eventually lands up in the oceans and impacts sea level rise. So if we look at the two main ice sheets, and here you can see this animation, you can see the date changing on the plot, and in the map you'll see the color changing. Here we can see the melting of the ice over Greenland, and this is measured by a pretty fancy satellite called GRACE, which is measuring actually the gravity, the pull of the Earth underneath the satellite. And as I mentioned, we have 3 or 4 kilometers of ice over Greenland. That's a huge mass. So if we're losing that mass, if it's melting and becoming water, the satellite can actually detect that. And the units here on the satellite are gigatons of water which are being lost every year and flowing into the oceans. And basically the slope of this curve shows that about 277 gigatons per year are being lost because of the melting of the ice on Greenland. You can see it's mainly around the coastal regions of Greenland. In the central part, we still don't have massive melting, but this is very worrying that we're seeing this rapid melting of the waters in Greenland. And we can compare this with Antarctica. So here again, we can see the animation is running with the dates, and we can see two curves here, the yellow and the blue curves. So the yellow curve is what we just saw for Greenland, and the blue curve is for Antarctica. The melting in Antarctica is a lot slower than in Greenland, but it's still, we're seeing a negative mass balance. It's a lot colder in Antarctica, and so things are changing slower in Antarctica. But there's enough water in the frozen ice on Antarctica and Greenland together to cause the sea level to go up by 70 meters all around the planet if everything melts and becomes water. That's huge. 70 meters, all the cities will be deeply underwater around the world if that happens. I hope it's not going to happen. But to put that in reference, we spoke about the last ice age. And the last ice age, the sea levels went down 100 meters because we had so much ice on the land. And so planet Earth doesn't really matter, doesn't really care if it goes down 100 meters, it goes up 70 meters. The big problem is us. We need to live with these changes. And if we can prevent them, then we should be preventing them because they're going to be huge implications otherwise because of sea level rise. So 85% of the world's land ice at the moment is sitting in Antarctica, about 10% in Greenland. I should point out that both of these locations, again, are in the polar regions where we have a little bit of solar radiation. There's also there, locally, we have very high pressure, atmospheric pressure, which doesn't encourage the formation of clouds and rain and snow. So these regions are actually, especially Antarctica, is a desert. The amount of rainfall or snowfall or equivalent rainfall in Antarctica is actually less than we get in Eilat every year in Israel. It's a desert. And so if we melt the ice, to bring it back can take us tens or thousands, if not longer, of years, because those regions don't get much snowfall. It's built up over hundreds of thousands of years, these ice sheets. And if we melt them, we basically have to live with that. We won't be able to replace it very easily. Talking about the last ice age, so we can see here the map of where we had ice sheets 18,000 years ago, close to the maximum of the last ice age compared with modern day. In the southern hemisphere, we're not showing because it was basically the same. Antarctica today is covered in ice. 20,000 years ago, it was also covered in ice. But the northern hemisphere was significantly different. We see here on the right-hand side, the modern day ice sheet is really only over Greenland, as well as the sea ice shown here in gray. And 18,000 years ago, the whole of northern Europe, Scandinavia, the whole of Canada, down to 37 degrees, which includes New York City, was underneath this ice sheet. So we had two additional big ice sheets back then, the Scandinavian ice sheet, which went down to about 48 degrees in Europe, and the Laurentide ice sheet, which went down again to 37 degrees in Canada and the United States. And as I mentioned, because the ocean volume seemed to have dropped by 4% 20,000 years ago, because we had so much ice on the land, the ocean sea level went down by 100 meters everywhere around the globe.